Welcome, everyone, and thank you for joining us at Coalesce 2021. My name is Amada Echeverria. I use she, her pronouns, and I'm a developer relations advocate on the community team at DBT Labs. I'm thrilled to be hosting today's session, Observability within DBT, presented by Kevin Chan and Jonathan Talmi. Kevin is a data engineer at Snap Commerce and helped scale the data platform from infancy. He's also one of the original developers of the DBT Snowflake Run operation macro. Fun fact about Kevin, he happens to have a tooth within his front tooth. And when he was very young, the baby version fell out and the adult version grew. Quite the hero's journey for Kevin's tooth. Jonathan Talmi is a data platform lead also at Snap Commerce. He is a researcher turned analyst turned data engineer and finally turned analytics engineer. An avid outdoors person, Jonathan has hiked across 2 whole countries. Using the DBT Run artifacts, Jonathan and Kevin were able to create a central monitoring and alerting system that notified people if a specific DBT model failed. And this is what our speakers will explore over the next 30 minutes we have together. Before we jump into things, some recommendations for making the best out of this session. All chat conversation is taking place in the Coalesce-DBT-Observability channel of DBT Slack. If you are not yet a part of DBT Slack community, you have time to join now. Seriously, go do it. Visit getdbt.com/community and search for Coalesce DBT Observability when you arrive. We encourage you to set up Slack and your browser side by side. In Slack, I think you'll have a great experience if you ask other attendees questions, make comments, share memes, or react in the channel at any point during Kevin and Jonathan's session. To kick us off, our chat champion, Ashley Murray, a software engineer at DBT Labs, has started a thread to have you introduce yourself. Let us know where you're calling in from, and tell us how you currently use DBT artifacts, if at all. After the session, Kevin and Jonathan will be available in Slack to answer questions. Let's get started. Over to you, Kevin and Jonathan.
Hey, everyone. Yeah, it's great to be here. Today, we're going to talk about observability within DBT. My name is Jonathan. I'm the data platform manager at Snap Commerce.
My name is Kevin. I'm a data engineer here at Snap Commerce.
Awesome. So let's get started. Just first, a little bit about the company. So the mission statement of the company is to provide access for everyone to experience more of what life has to offer, regardless of income or circumstance. Now, what that actually means is we've built a new way to shop that maximizes savings, benefits, and rewards on mobile. And this roughly translates into started with hotel bookings and consumer goods, but with plans for much more. And so far, we've driven nearly $1 billion in sales using our platform. So about myself, I'm the data platform lead or manager here, and I got my start doing research, academic research, before migrating to the tech industry, and had a winding path to find myself really thriving in that analytics engineering space. And yeah, Kevin, you can introduce yourself.
My experience is heavily in data engineering, as well as some machine learning engineering and deployment. Recent graduation from Waterloo as well, from computer science and statistics. Previously, I worked at Hootsuite and Splunk before I found my way back here at Snap Commerce.
Cool. Data observability is obviously a really large topic. The number of use cases for data within individual companies, as probably everybody here knows, has grown exponentially over the last few years. Data platforms serve not only classical BI use cases, but power data science, real-time analytics, experimentation, and more. And the modern data stack, while we love it and cherish it, has made data platforms even more fragmented than before. So the surface area of data systems has increased. The need for observability into these systems grows. Now there's even a lot of companies focused specifically on observability and reliability, like Metaplane or Monte Carlo. And there's the data observability space is growing really fast, and it's pretty multifaceted as a whole. So this talk specifically is going to focus on how to get more observability out of DBT specifically, using the tools that you already have in your stack. Now, why does observability matter? The need for observability within DBT becomes apparent when you start getting questions that you can't answer within a reasonable time frame. So these questions might be something like, why isn't my model up to date? Is my data accurate? Why is my model taking so long to run? How do I speed up my DBT pipelines? how should I materialize and provision my model? So as you can see, observability is particularly critical during periods of data downtime where your data is partial or erroneous or missing or inaccurate. Now, when we couldn't answer these questions, we realized that we had limited observability into our own dbt deployment, and we had to do something about that. So this gave us a mandate to build a system that would help us perform a few jobs that would give analytics engineers their desired observability into dbt. First, we wanted to send alerts to dbt model owners and stakeholders based on custom criteria. So model owners should know when their specific models or test fails, or when their sources are not fresh. Second, we wanted to surface data that would help analytics engineers optimize their models and identify pipeline bottlenecks. And third, we wanted to reliably collect all of this metadata and action it in close to real time, regardless of the success or failure of the dbt pipeline. Our guiding principles for this project as engineers were keeping the system lightweight so that it could be easily deployed on our stack, which is a modern data stack. We wanted to surface all the relevant artifacts and metadata to enable SQL-based alerting and exploration. And finally, we wanted to support all dbt resources and artifacts and all job types like run, test, build, etc. So we thought that dbt artifacts might serve as a good foundation for this system since they contain pretty granular information about dbt executions. For one, dbt tests are an interface for defining data quality metrics and are often the first line of defense when you're identifying disruptions. And artifacts themselves store the results of model and test failures. dbt artifacts also store information about when models get built and how long they take, which can help you identify bottlenecks in underperforming models. So we came up with 3 data sources to build our system. Now, the first is the project manifest, which gives you the full configuration of the dbt project. The second are the run results artifacts that get triggered after you do a dbt run or test or other commands. These give you detailed node and pipeline level execution data for models, tests, and other resources. Finally, we looked at the Snowflake query history as Snowflake users, which gives you rich query performance metrics that you can tie to individual models. We ultimately found that joining the artifacts and the query history together actually gave us deeper insights about model level performance than we would have had if we just used the artifacts alone. Now I'll hand it over to Kevin, who's going to discuss the architecture and solution.
So at a high level, the solution that we built can be really divided into 5 components. And effectively what we built out is a very lightweight ELT system that ingests the artifact data into our data storage. So the first component is the orchestration. We use Airflow as our workflow orchestrator. And within Airflow, your workflow is represented, each task in your workflow is represented as an operator. And effectively, we use the Kubernetes pod operator to spin up a Kubernetes pod to execute our dbt tasks. With every dbt command, such as dbt run, dbt test, there are artifacts generated associated that are stored on local disk, or in our case, the Kubernetes pod operator. We needed a way to load the data from this pod into our data storage, which in our case is Snowflake, at the end of every dbt pipeline. So once we have the pure raw data in our data storage, that's when we can begin to use dbt to parse out the nested JSON, parse out the structure, or parse out the metadata we need associated for dashboards downstream, and effectively merge the run results with the query history in Snowflake to generate even more metadata and more information regarding our pipelines. The fourth component is reporting. So once we have effectively transformed the data and create a structure that we can work with, that's when we can start to build dashboards upon it and take a look at how our pipelines are doing, what models have failed, what tests are failing, how long have these models been executed. And by merging it with the query history in Snowflake, we can take a look at how many bytes of data are spilled onto disk, what is the credit usage in Snowflake. And finally, within these dashboards in Looker, we're actually able to create alerts on them to say, okay, if our status has changed within the last 15 minutes and the model has failed, let's send the alert to Slack. And we've effectively done so by creating Slack user groups to alert individual model owners if their dbt test or model has failed. So let's go into a deeper dive about each of the components. All of our dbt pipelines are centralized in Airflow, with the exception, of course, some of the ad hoc jobs. We still have dbt cloud, and a use case for this would be, say we want to refresh an incremental model at X point in time. The code piece snippet below is an example of how we instantiate the Kubernetes pod operator in Airflow. We do have some default configurations, which are more so just the CPU usage, the resource allocation for each pod, as well as where the image lives. Within every model within our deployment has one deployment tag. These are hourly, nightly, and external. So the image showcases below are our hourly, nightly runs. Note that every widget or node in this graph is effectively one invocation of dbt. So for example, the two tasks at the very beginning are dbt run commands. The following are snapshot, and finally the test. And for models that are tagged external, it just means that they're not part of our hourly or nightly runs. Instead, what we do is for pipelines where we want to run the transformations as soon as the data lands, that's when once the data is loaded into our data storage, that's when we want to begin to run our dbt transformations, and that's the perfect use case for our external tag. We use intersection selectors to avoid race conditions so that we're not effectively building a model that is existing in our hourly or nightly runs. So once we have orchestration, we have a place at which we can execute our dbt commands. The next step is let's load this data into our data storage. Effectively, we built out a dbt macro in order for us to do so. The first step of this is the put query. What that does, it loads the file from your local disk onto an external stage in Snowflake. Think of this as an external cloud storage where Snowflake can effectively query that file. The next command is the copy command. What that does is it loads the data from, it quite literally copies the contents of that file that you uploaded to the stage into a destination table. We've created destination tables for the major artifacts, such as the run results, the dbt test run results, as well as the manifests. And the final command is the remove query. That just removes the file that you uploaded into the external stage from, and all of this can be executed using the dbt run operation. So the first command that we've shown is the dbt run that runs all of our models tagged hourly. And then following command is the run operation that runs the macro that we've built out to upload the artifacts into Snowflake. The beauty of this is that this also executes even after a dbt job failure, because we also want to load the artifacts if the run has failed. The next component is the modeling. Once we have the raw data in Snowflake, let's begin to use dbt to transform this data set into different models that can really power our dashboards downstream. So note that all the green nodes are our sources. We do have run results, test run results, and manifests. One key note is that one of our sources is also the query history table in Snowflake. We've effectively merged that with the run results to generate a table that contains credit usage per query, byte spillage onto disk, as well as the warehouse sizing per model. Also take note that all of these transformations are heavily based on the repo by GitLab. Their repo is open source. You can take a look. All of our staging models power the downstream dashboards and as well as the fact table that we've created. So glossed over the transformations, now we have onto the reporting that we've created. This is an example of a dashboard that we've created in Looker. And if you go from left to right of the columns, the model name is what we've parsed out from the artifact metadata. The status, of course, is if the model has failed to compile or not. Generate timestamp is when the artifact was truly generated, and that's what we can focus our alerting on. The next one is the model error text. So with every model failure, there's also the error associated with that. So we can have it in a table that we can view and send to stakeholders to help us debug our data pipelines. The tags are the tags associated with the model. And finally, the fresh failed run is what we actually use to set up the alerting associated. If that value changes in a 15-minute time span, that's when we are able to send an alert to Slack. The next component these are the test results. This is a dashboard specifically for our risk test results. Similar structure to our finance runs. The only key difference with this is that we have the compiled SQL as the very rightmost column. That contains a SQL that you can execute on the data warehouse to effectively run the same test that was run during the dbt test. The test name also has the type of test embedded within the name, such as a not null or a unique test. And finally, the alerting component. So that fresh failed run component that we've set up is what we use to send Slack alerts. You'll notice that we have these domain-specific tags. Every model within our dbt deployment has one domain tag, and these can be growth, product, or finance, or catalog, etc. These tags are what we effectively use to filter to create these dashboards. For example, in the previous slide, we have the latest risk run results. So again, you just filter out for the tag risk. And within Slack, we're able to create these user groups. So within these user groups, we can add people to them. So When we send the Slack alert tagging everyone from growth, everyone who is part of that domain will receive this alert and we'll be pinged in Slack. Whenever their model fails that they own, they'll be able to debug accordingly instead of notifying everyone in the company or anyone on the data team who has a model in dbt.
Cool. So Kevin just demonstrated how we use this system to power our success and failure alerting and dashboards, which is extremely useful. I'm going to talk a bit about how we use this data for performance management. So this chart shows that the performance data for some long-running models taken from the artifacts and joined to the query history in that combined view. You can see that there's several actionable pieces of information here. First, if a model is taking a really long time to build, and an engineer can consider adopting a new materialization strategy, like maybe it's time to make that model incremental or insert by period. Second, if the model has a high percentage of total partition scan, which is a Snowflake metadata field, then they might want to explore updating or adding clustering, because for certain models, it's not a good sign if they're scanning the entire table when rebuilding. Finally, if the model tends to have a lot of spillage and bytes sent over the network, that might be a sign that it's time to increase the size of the warehouse once other opportunities for optimization, like refactoring the SQL or anything else, have been exhausted. So overall, this type of view can be very useful for people to get a sort of a bird's eye view of their models and their domain and how well they're performing. So you can also take a look at that previous view and look at an individual model over time. I'll show you a couple of views that you might find interesting. This animation here shows you a single model and the execution time and all the other metrics in the time series view. So you can see that this model has been growing and growing in terms of overall execution over the course of the last couple of months. And similarly, you can look at other views for model executions over time. So the top one is probably an hourly model. You can see that it's triggered quite a lot, but the execution time is relatively over the last little while. And at the bottom, it's most likely a model that gets run once a day. And you can see that it's starting to trend up over time. And eventually, it might be worth taking a closer look at this model. Finally, the last set of visualizations I'll show you are visualizations that allow people to look at dbt pipelines as a whole. So this slide shows two Gantt charts, one each for the hourly and the nightly dbt model run pipelines. On the y-axis, you have thread number. On the x-axis, you have time. Definitely got to shout out Claire and Drew for inspiring this visualization with their artifacts discourse posts. So these views can help us identify bottlenecks and candidates for optimization when the pipelines start to get out of SLA. So for example, if your hourly job starts to take longer than an hour, or your nightly job is taking several hours and is starting to affect other downstream pipelines, then you might want to take a look at this and identify the bottlenecks and work on specifically on those models and optimizing them. For example, in the nightly run here, you can see there's one model that's really holding up a lot of other ones and pushing the entire pipeline execution time farther out. And this last visualization is the same view as before, but for tests, and I pretty much included it because I thought it looked really cool. How can you implement this yourself? Well, everything that we showed you is highly interchangeable. You can deploy this easily on the modern data stack using any BI tool, any alerting tool, any orchestration tool. Really, every piece of it is interchangeable. Specifically for alerting, you can alert through BI, or you can look at, there was a dbt community member who published this library here called Snowflake to Slack, which would allow you to trigger these alerts directly, for example, Airflow or any other orchestration tool. And then when it comes to modeling the dbt artifact, you don't have to build it ourselves like we did or the GitLab folks did right now, because now there's a package called from the Tails team called dbt artifacts that does pretty much a lot of this for you. So this didn't exist at the time that we set out. And finally, definitely we encourage everyone to use dbt Cloud. Now they have a robust metadata API. They're even building visualizations and other features directly into the tool, like the bottleneck diagram shown below. So it's in terms of from a metadata perspective, they're doing a lot of great work there. And yeah, that about wraps it up. We really appreciate everybody coming in and listening to our talk, and just want to remind everyone that if you thought that any of what you saw here today was cool and you would want to work on similar and even different projects, definitely give me or Kevin a shout. We're hiring across data, and we love to chat about this. Email us, dbt Slack, LinkedIn, anything works. And yeah, thanks a lot to everybody attending. Thanks a lot to Ashley, Amada, and Bar specifically for helping us with our presentation. And yeah, it's great to be here.